can go back and review these if you choose to see what the things that we did. So the first set of problems here that we're looking at are problems that we're dealing with wording. So it's giving us a description of a chemical reaction, and we have to go from the name of the compound to the chemical formula, and once we do that, we have to balance the reaction. So we've got to understand our naming stuff from chapter 3 and then go forward from that. So, all right, so it tells us nitric acid is a component of acid rain. It forms when we have gaseous nitrogen dioxide. All right, so that's one reactant that reacts with gaseous oxygen and liquid water to form aqueous nitric acid. So there's 3 reactants in this one, and the product is the nitric acids. So let's just start trying to figure out formulas. So what is nitrogen dioxide? Give me a formula. Okay, NO2. And it tells me it's gaseous, so I'm going to put a G after it. All right, the next reaction is oxygen. So we know what O2 is. And then it tells me liquid water, H2O. And it tells me liquid state. And then it forms nitric acid. So nitric acid is one of the acids we needed to memorize. And it tells me that that's aqueous. So this is one of the ways that the pollutant nitrogen dioxide gets converted into nitric acid in acid rain. Okay, now I need to kind of look at an atom inventory and see if the reaction's balanced. If it's not, I need to balance it. So if I look at the nitrogens, I've got 1 nitrogen on the left, 1 nitrogen on the right. That looks okay. But when I look at the hydrogens, I already see that there's 2 hydrogens on the left, only 1 on the right. There's a mismatch. So on looking at balancing this one, it's a little bit more complex because there's 3 reactants, but always save the oxygen for last. So let's try to figure out, let's try some attempts to balance it. So what should I try? Okay, start with the hydrogens. Let's say there's 2 hydrogens on the left. We'd make it 2 on the right. We can try there. Okay, so if we got 2 hydrogens on the right, that balances the hydrogens. Now, if that's going to balance 2 hydrogens, we're going to save oxygen for last because it's the one that's independent. So save that as the last thing to balance. So now we need to go to the nitrogens. So 2 nitrogens now on the right. To get 2 on the right, I'd have to do that. Or 2 on the left, I'd have to balance that. So where does that leave me on oxygens? 7 on the left. Okay. And there's 6 on the right. So we can't take 1 away. So what else might we try? So we tried something. We didn't come up with a solution. Let's try something else. So let's just take those 2 off. Okay. What else you want to try? Try what now? Okay, so we can try that. So why do you want to do it by 4?
We came out to where you had 7 oxygens on the left, 6 on the right, and then the O2 there. Like, you could say that you multiply it by half to get 1 oxygen, but you multiply the right by 2, maybe put that there.
Okay, so put this coefficient right? Is that what you're saying? All right, so if we do the same thing, if we go 4 here, all right, that means nitrogen's 4. That means we're going to have a 4 in front of this one. So now if I look at the number of oxygens that are on the right-hand side, I've got 12. So our nitrogens are at 4. So I've got oxygens 4 times 3 is 12. Oxygens here, 4 times 2 is 8. And if I look at hydrogens, I need to balance out the hydrogens before I can do the oxygens. So I've got the number of hydrogens on the right is 4. So the number of waters, that would have to be 2. So that gives me 4 on this side. All right, so now maybe I can balance out those oxygens. So again, we've got 12 oxygens on the right. We've got 8, and 2 is 10. We need 2 more, and that would be, if this is a 1, that would make that a 2. All right, so I think that's a balanced reaction. So nitrogens, so count again. Nitrogens, I've got 4 and 4. That's good. Oxygens, 4 times 2. 8 plus 2 plus 2, 12. That's good. And then hydrogens, 4 and 4. So look. So you try something. If it doesn't work, try something else. Okay. So that's the reason. Write those in pencil. You erase those coefficients. So sometimes it's not obvious. We kind of learned from the first one when we started with the 2 there. We found out it wasn't big enough. It didn't give us enough oxygens on this side to accommodate what was over here. So that's kind of one of the things you could look at, is that initially, if everything's a 1, there's at least 5 oxygens on the left-hand side. So that's going to have to be 2 or greater over here. Okay, so you just have to play with it. Okay, so when iron rusts, it says that iron solid reacts with gaseous oxygen to form solid iron 3 oxide. So I've got iron solid plus gaseous oxygen. All right, so give me the formula for iron 3 oxide. So if it's going to be Fe3, what's the charge of the oxygen? That's a -2 because it's in the 2A family. And then if you do the crossover rule, it would be a 2 and a 3. So Fe2O3. All right, so that's a solid for the rust. Okay, so if I look at balancing this one, I would start with, look at the number of irons, save the oxygen for last. So this is only 2 elements, so it's not going to be too bad. So I've got 2 irons on the right. I need 2 on the left. I have 3 oxygens on the right, and I need 3 on the left. So the way that I have to do that would be 3 halves. But the author says that he doesn't like the halves, so he wants us to multiply everything by 2. Get rid of the halves. So if I multiply everything by 2 all the way through, this becomes 4. This gets rid of the half. It just becomes 3. And this becomes 2. All right, check my atom inventory. Make sure that everything's good. So I've got 4 irons on the left. I've got 4 irons on the right. Oxygens, I've got 3 times 2. I've got 6 on the left. 2 times 3, 6 on the right. We're good. Okay. And again, the author's view is he doesn't want anything fractional. He wants us to get rid of those fractions. Got a question? Y'all figure it out. Okay. All right, let's look at the next one. Okay, let's write the balance reaction for photosynthesis that involves gaseous carbon dioxide. So carbon dioxide, we've talked about this one a bunch. CO2 plus liquid water in the presence of chlorophyll to produce aqueous glucose. Glucose is C6H12O6. So aqueous plus O2. So that's what we want trees to do. Okay, so looking at what to balance on this one, again, I'm going to save the oxygen for last. So anytime you've got an element by itself, save it for last. Okay, so if I start with the most complex compound, that's the glucose molecule. So it has 6 carbons. I'm going to say, let's put a 6 in front of the carbon dioxide. So that's 6 carbons. Now, if I look at the number of hydrogens that go with that, on the right-hand side, I've got 12. I've got a water molecule. It's got 2 hydrogens, so I need to put a 6 in front of that. Okay, so now I need to look at the oxygen. So this is, we're saying that's 1. So how many oxygens do I have on the right-hand side? Okay, so on the right-hand side, I've got 2 different sources. There's 8 oxygens over here. How many are on the left-hand side? So I've got 6 times 2 is 12, plus 6, 18. So I need to add 10 more oxygens to this side to get to 18. So I've got 6 here. What would I have to do to make this 18 total? Okay, so I'd have to add 12 oxygens by doing a 6 in front of that. So that's 6 plus 12. That'd give me my 18 on this side. I've got 18 on the other side. The carbon 6, the hydrogens 12, hydrogens 12. So that gives me a balanced reaction. Okay, so just a couple more of these. We'll do 2 of these. Let's do the first one. It says solid copper reacts with solid sulfur to form solid copper 1 sulfide. So if it's copper 1, so the 1 tells me it's plus 1. What's the charge on the sulfur? It's a -2. Okay, it's in the 6A family, so 6 minus 8 is minus 2. So when I write the formula, I'm going to use the crossover rule. It would be Cu2S. Say again? Yeah, it tells us a solid. It is a solid phase. Okay, so this one may not be too bad to balance. I look at the elements that are there. I've got 2 coppers on the right. Put 2 coppers on the left. I've got 1 sulfur on the left and 1 on the right. It's too easy to ever give you on a test. Y'all want more challenging things than that. Okay, let's do C. So I've got sulfur dioxide gas. All right, plus oxygen gas to form sulfur trioxide gas. Okay, so that's my components of my reaction. So looking at the sulfur, there's 1 sulfur on the left, there's 1 sulfur on the right. But if I look at the oxygen, I've already got 4 oxygens on the left, and I've got 3 on the right, so that's not going to work to add numbers of oxygens, or would it? Okay, is there a way I could make this 1 oxygen, though? If I wanted 1 oxygen atom out of it? Okay, so I'll come back and I'll do the your way, but let's try it this way first. So if we put a 2 or 1/2 in front of that, that would give me my 1 more oxygen. Okay, so that would give me 3 oxygens, 1 oxygen, 3. That are 2 oxygens, 1 oxygen, so that gives me my 3. But if we get rid of our 1/2 by multiplying everything by 2, we're going to be to where you're suggesting. So multiply everything by 2. That just becomes 1. So now it becomes 2 to 1 to 2. So if I do my atom inventory on the sulfurs, I've got 2 sulfurs on the left, 2 sulfurs on the right. The oxygens, I've got 2 times 2 is 4, plus 2, 6 on the left, 2 times 3, 6 on the right. So if you see it to go ahead and put a 2 in front of everything, that's okay. But if you want to make it at 1/2, still your goal is to get rid of the fractions at the end. You'll end up the same place at the end. Okay? All right, these are just balancing. So what would we have to do to balance a couple of these? All right, let's look at the first one. I don't know why they have double letters on them, but they do. Okay, so the thing that I'll tell you with these is that they involve polyatomic ions. So instead of counting every atom individually, like the nitrogens and the oxygens, realize the polyatomic ions stay together. So they don't separate from one another. So the NO3s, I can just count that like an element X. They're going to stay together as an intact polyatomic ion. Everything else is elemental. But if I look at this one and just think about that polyatomic ion, there's 2 of them on this side. That means if they're here, I'd have to have a 2 in front of that, in front of the sodium nitrate. Okay, so other elements that I have, I've got, if I just make that 2, that gives me my 2 sodiums. I've got 1 sulfur, 1 sulfur, 1 copper, 1 copper. That balances just by adding that simple 2. Okay, and the polyatomic ions, if you recognize that, that just makes life a little easier. All right, the second one, let's take a look at it. So I've got N2H4 yields N3H ammonia plus N2. Okay, so I've got 5 nitrogens on the left. I've got only 5 nitrogens on the 3 nitrogens. Got to count right. I've got 3 nitrogens on the right, 2 on the left. So what might we try to do to that? One of the things I see is we're going to have to find that there's only one source of hydrogen in each of those. And one has 4 atoms, one has 3 atoms. So we're going to have to find a common denominator. And that's going to be 12. Okay, so I'm going to take it to 12 to get it on 12 of each side. So to do that, I'm going to have to put a 3 in front of this one and a 4 in front of this one. Let's see if that will get us anywhere. All right, so if I do that, that gives me 12 hydrogens on the left, 12 hydrogens on the right. And in terms of nitrogen, I've got 3 times 2. I've got 6 on the left, and I've got 4 and 2, 6 on the right. That balances. Okay. We'll do D as our last one. All right, so I've got FeS plus HCl yields FeCl2 plus H2S. Okay, there's no single or monoatomic, so there's no really one atom you would say for last on this one. You just have to start looking at formulas and see what you can come up with. All right. Now, the fact that this has the most atoms in it, well, actually, both of these have 3, but this one has 2, so if I think I'm going to have a 2 on this side, that will give me 2 chlorines and 2 chlorines. All right. On iron atoms, I've got 1 on the left, 1 on the right. Sulfurs, I've got 1 on the left, 1 on the right. And the last thing is the hydrogens. I've got 2 on the left, 2 on the right. Balanced. So sometimes it's just changing one coefficient, putting the 2 in front of the HCl. Balances that one out. Okay. The next one. So classify as organic or inorganic. So things that contain primarily carbon and hydrogen are organics. So these are straightforward. So organic, no carbon in that. So that's an I for inorganic. The carbon that's in this is in the form of a polyatomic ion. It's an ionic compound. So that's an inorganic. Organics are molecular compounds.
part again? Said organics are, they have carbon in them?
Okay, so typically inorganics don't have carbon in them exclusively, not carbon and hydrogen. But you look at the example of the second one, that has carbon in the form of carbonate, but it's not a molecular compound. It's an ionic compound.
So organic are molecular compounds with carbon.
That's correct. Carbon and hydrogen primarily. But carbon's the key to make that. So the key thing on this one is to realize this is the polyatomic ion, carbonate, iron 2 plus. That's an ionic compound. And the other way to remember it is metal and nonmetals. Okay, so you've got a metal combined with a polyatomic ion. And the two things together make a ionic compound. Right, classify as an alkane, an alkyne, or an alkene. So I'm just going to show this underneath the naming because it makes them all obvious. Alkynes have triple bonds. Alkenes have double bonds. Alkanes are all single bonds. So that's obvious which one's which once you know that. All right, the last one we had was classifying organic compounds based on their functional groups, so identify the family. So if it had a C double bond O, OH, that is a carboxylate or carboxylic acid. If it had a C double bond OH, it's classified as an aldehyde. All right. If it just contains carbons and hydrogens in single bonds, that's an alkane. If it contains a C-O-C bond, that's an ether. All right, so that's all the problems that we have for chapter 4.
Those last things.
You did. That was one of the tables where we just have to fight through. So, all right, I'm on to go ahead and